Hello, good morning, everyone. Hopefully this is, you know, a good time for everyone. If you've never been to a Spack tutorial in the first place, you are joining at a very good time. We just released 1.0. This is the first tutorial we're giving based off of the 1.0 material. And so a lot of that is, many long-awaited features such as compilers as dependencies. Um, and we'll get into all of that very shortly. So welcome and hello, welcome to the world of Spack. My name is Alex Scott. I'm going to be giving the introduction today, and then I'm going to be followed by Kathleen Shea, who's going to be presenting on some of the basics of Spack utilization, and then Greg Becker to talk concepts, Caetano Malone, Tammy, and Peter Scheibel will all be speaking either today or tomorrow in part one or part two. So this is me and all of my co-hosts. We're all here at Livermore, and so if you are also at Livermore, feel free to, shout out and come say hi, visit us in person someday. And let us know if you find bugs with Spack after you get started using it. All of the tutorial materials for this are up online. It's spack-tutorial.readthedocs.io. There's going to be a lot of sections where we are working in tandem, kind of following the docs and doing some hands-on material. And so feel free to go to that link, pull up the documentation, and we should be able to, you can follow along at your own rate. You're welcome to come back to those docs. We have a container image, which I will be pushing up just very shortly. We've got a bunch of virtual machines that we're going to use for these tutorials specifically, but you're welcome to come back to this this website at any point to refresh your knowledge or just go through the tutorial again. Make sure to join the Slack channel. WebEx is kind of bad at trying to do threaded responses, so if many people ask interesting questions, we want to get to all of them. So feel free to go to slack.spack.io and then join the tutorial channel. Myself, as well as many of the other presenters here today, are going to be monitoring that and should be answering questions. I can also have them chime in the case that somebody asks a really good question and we want to cover it live as one of us is presenting. You can also continue asking questions there after this tutorial is over. That Slack currently has over 3,800 people. It is a great community resource, especially if you are just getting started with Spack, so that you can start to see what other folks are doing with the product or with the piece of software and, answer common questions that we get often. For all of those hands-on sections that I just talked about, we're going to be using virtual machine instances. To go claim a login for the VM, you can go to this link, bit.ly/spack-vms. If you want, you can also point your phone or take a screenshot or something of that QR code. It'll take you to the same link. There is a Google Sheet. The Google Sheet has a whole list of IP addresses there on the left. And then on the top, basically your header rows, those are going to be your username. The IP address is what you're going to be logging into. And so you can SSH into those by doing username at instance. The password is the same as your username. So spack1, 2, 3, etc. If you were on Livermore's site or on the Livermore VPN, you're going to have to open up an EOR request with CSP. Maybe Christy or David can give a little bit more information on that in the chat for folks if you need the URL or something. But if you submit an EOR request, if you're on site, that typically takes 5 to 10 minutes to go through. So great time to do it now. So I probably wouldn't recommend, I just had a question about using your own machine. We probably wouldn't recommend using your own machine because we've built a lot of binary caches into these VMs so that a lot of the demos go more quickly. You are welcome to do all of this on, you're welcome to do this on your own machine. It's just going to take a lot longer to build everything from source, and you might get a little bit further behind. But you are welcome to, go back after you've learned this on a VM and then apply it to your own machine or one of the Livermore clusters.
If you try to do it on your own machine, you'll end up something like 10 hours behind by the end of the tutorial. So really recommend using the VMs.
Yeah. Okay, so this is an approximate agenda. We're here in day one. We're going to be going through, really the bootstrap to getting started to using Spack the very first time. So the basics, some of the concepts that Greg will lay out. We're going to have, I guess, just a quick 5-minute break, and then we'll be doing environments and configuration, and then ending up around noon. We're happy to stay on a little bit later if people have questions, but don't want to take everyone else's day up. Then we'll be rejoining tomorrow at 9 a.m. Pacific. We're going to be talking about software stacks. This is really how you parameterize your installs, as well as how to become a package creator and a package maintainer. How to write your own Spack packages. We'll again then have a little break, and then we'll be talking about developer workflows, mirrors and binary caches, and I forgot to put one other session on here, scripting, if we have time for it. Where you can get into more of the advanced usage of Spack as a Python SDK. So you can start using Spack from within Python programs. As everyone here is, probably well aware, modern scientific codes are not, uniform pieces of software that cover everything all the way up the stack, right? We are really not well vertically integrated, and that's a good thing. We make use of many, many different libraries, and each of those libraries are scoped to a specific piece of physics, a specific piece of software, or numeric calculations. And the problem with that really is trying to integrate all of these libraries, all of these pieces of software into a coherent large scale application, like some of our physics simulations at the lab. It allows for greater cross collaboration across institutions, across different teams, even inside of the same lab, but it causes a bunch of problems. When we're moving at such a high velocity, how do we integrate these ever updating libraries into our codes? And so just kind of to talk about some of, how big some of these simulation codes have gotten, we have MFEM, often used in HPC, right? MFEM depends on 69 things in total. It's 31 different packages in the spec, but let's get even bigger. So we have LBAN. This is a product out of Livermore for training neural networks on HPC. LBAN has 188 dependencies, and you can map that by 71 packages inside of Spack. But let's go, way bigger. So RCondup is a genome analysis tool, and it's got 179 packages in Spack. And you can see this is the dependency graph. And so really, when we start to use Spack for large simulations and large code bases, we're talking about an immense amount of complexity here, where Spack can help you do the heavy lifting so that you don't have to go manually integrate all of these libraries just to build your single piece of software on top of them. Spack really grew up inside of ECP. This is ECP's E4S stack. It's even larger than all of those codes. It's kind of hard to see in this diagram, but all of these red boxes up here, they are kind of the quote ECP stack. And then all of these blue-gray boxes are everything else that you need to build it. And so ECP was supposed to be one coherent stack for the exascale computing program that came out of the Department of Energy. It is impossible to try to keep this thing, try and integrate and keep all of this up to date if we didn't have tools like Spack and other package managers to do, coordinate all of the builds, coordinate all of the linking. We'll talk about how Spack uses RPaths to point at specific dependencies a little bit later on. But a lot of this would be an impossible task. It's also made harder by a lot of our, I mean, it's really good that we use open source. A lot of our projects, both at the lab and across the world globally, are using open source software to reduce, I guess, duplicated work across different institutions, right? It's great that we can submit our code, push it out there, and create a global community that all can work on the same piece of software rather than having to create Livermore's specific version of one library, or Oak Ridge's version of a specific library, or Riken's specific version of a library in Japan. we can collaborate as a large community, but this also adds additional complexity. This is a dependency graph for Aries, which is a large simulation code at the lab. And Aries depends on a lot of open source software. As you can see, all of these light blue boxes are external open source software. So this is everything from package config to Python, MPI, etc. Then we have in yellow kind of all of the Livermore open source codes that we support and that we push out into the world. And then the pink are all of the proprietary libraries that Livermore does not release publicly. This means, though, that there's a lot of velocity moving across. You're trying to coordinate with a global community, you're trying to coordinate inside of the lab, and you're trying to coordinate just on a single project using all of these libraries. So Spack is really about helping to put all of these together in a sane and coherent way. Hopefully now I've made that point a number of different times, and it'll help a little bit. So folks often ask us, like why Spack? Why not another package manager? And a little bit of that is that other package managers sometimes make, common but questionable assumptions about software. Many of them, such as Debian, suppose that you have a one-to-one relationship between your source code and your binary. So on Debian, if you go use Ubuntu or Debian Linux, right, you're getting one binary package for, let's say, SSH or for OpenSSL or Emacs. Inside of HPC systems, we oftentimes want to create variants of different software, and we want to optimize that software for specific architectures. Many of these large-scale distributions, including Red Hat, Debian, Ubuntu, their goal is to create binaries so that it's easy and very quick to install the operating systems on as much hardware as possible. And that's great, but we also want to, as I was just talking about, performance optimization. Oftentimes in HPC systems, we want to build the software for the specific libraries that are installed on a supercomputer so that we can make that software as fast as possible. We also sometimes want to build packages with many different tool chains. And what I mean by that is, different sets of compilers such as GCC or Intel One API, or on our machines at Livermore right now, like the Cray PE. We want to use these compilers that are well optimized to the machines, or we might want to compare and benchmark different compilers and different versions of libraries such as MPI with OpenMPI and MPitch. We might want to benchmark them and compare them for a specific code. So we want to build a lot of these packages in many different ways. This is a lot of what I was just talking about. As you can see, like Livermore, we have LCAP these days. LCAP is an MI300. Oak Ridge is an MI250. Those are pretty similar. They're both still x86, the instruction set that probably most folks here have worked in. But then we have supercomputers such as Fugaku at Riken in Japan. Fugaku is an ARM machine, and it's using the A64FX kind of vectorized accelerated instructions. If we were to try to build a portable binary across all of these different machines, we would get really bad performance, right? Because we'd have to back off to something that couldn't make use of the fancy vector instructions in Fugaku or the nice fancy vector instructions that we get in AMD Zen on Livermore or Oak Ridge. We oftentimes also rely heavily on these kind of low-level dependencies, such as the MPI that we have on the Cray machines integrates very well into Slingshot, which is the network fabric. And so oftentimes we want to build our software on top of very specific sets of libraries. And so Spack allows us to do this. We often also get folks asking, what about containers? Why can't I just build up a container for every different supercomputer? You can. It's not trivial. Spack actually can help you build containers. And again, containers mostly use the OS package manager inside. You're doing something like an apt install or a DNF install inside of your container. You're still getting those unoptimized binaries. If you were to build everything up from source inside of a container, that's great. You're doing very similar work to what Spack is doing in isolating your dependencies around from each other. And containers are very portable in one sense that like there's a lot of great tooling out there to pull them down and push them up from registries. Um, but as a result, you get a lot of kind of duplication across containers, where Spack is able to mix and match on the individual package basis. You often need to have a custom container that has either everything you could possibly need in it to run on a machine, or you're going to have to create a container per application per a specific type of machine. And so this is really where Spack comes in, at least for us, as kind of a better or an equivalently good solution for most things, if not way better for most. Spack allows us to automate the build and installation of scientific software using a parameterizable language that Greg is going to get into later on in concepts, and you'll see a bit of in basics with Kathleen here shortly. Um, you can just go ahead and clone Spack. We're going to do this very shortly in basics, so don't feel need to do it right at the moment. But you can clone Spack, and then you can activate Spack. It's just a Python package. And from there, Spack will allow you to build all sorts of software targeted, very specifically at the type of machine that you're running on, whether that be your laptop or the supercomputer. And we have these abstract I guess these abstract syntax that we call specs or abstract specs here that is shown in the second box. Those abstract specs allow you kind of this level of portability where you can take the same abstract spec, you can share it between your laptop, between a supercomputer, and then we do a process called concretization where we go figure out all of the dependencies, how we're going to reuse the different libraries that are already installed on a machine. Then you get a different concrete spec for your laptop and for a supercomputer or between two supercomputers. But you essentially still got to put in the same input, and you got two different outputs that are optimized to the two different places that you want to run. We also support environments, kind of like Conda or Python's virtual environments. We'll dive into that a little bit later in this presentation as well. And we've got support for a lot of DevOps features. So Spack can be run in a build farm inside of GitLab. We can generate containers, as I was talking about earlier. We're going to get into a lot of that in this tutorial. So, heads up, and hopefully you guys learned some kind of interesting stuff there. If I've been rambling on about package managers and you're really curious, okay, what is a package manager? So Spack is a package manager. So is apt, so is DNF. A package manager does not replace something like CMake, like Make, like Auto Tools. It is really the coordination between many different discrete libraries. And so Spack manages all of these dependencies, and it's aware of this tree of dependencies of how different libraries relate and depend on each other, allowing us to kind of model the whole software ecosystem and the whole software stack that you want to install somewhere. Um, so you can see like, low-level build systems are Make and Ninja, CMake and Auto Tools build on top of that. And you can really think of a package manager as an abstraction even on top of that, where it knows about the specific dependencies. And so it's going to inject the right paths into something like CMake or Auto Tools. It's going to be able to tell you whether you're configured with MPI or not, if your system supports MPI or not. A lot of kind of the higher level modeling of the ecosystem. So who can use Spack? Spack is honestly for everyone. I even use Spack on my laptop. I might be a little bit weird, but it is totally doable as like a homebrew replacement for Macs these days. But Spack is really for a lot of different people. It's for us developers who want to get running on an HPC without going and talking to the system administrators to have them go and install new modules for you. You can have Spack build your own modules. You can tweak your own modules, and then you can share and publish kind of what you've installed when you go and publish a paper so that other people can reproduce your results by taking that same, in this case, we'll probably end up using environments. You can take that environment, you can share it when you publish a paper and allow people to reproduce your study. It's also for those HPC application teams, those system administrators who want to go provision a new HPC machine. And so this really allows you to make use of Spack's abstractions and a lot of the DevOpsy functionality of Spack to simplify your deployment processes by creating a list of different libraries and tools that your end users want installed, and then say, hey, Spack, go figure out all the permutations with all the different types of MPI, and go figure it out with all the different compilers that I want to run. And Spack will just go off and build the cross product of all those different options for you. We'll see that in the stacks section tomorrow morning. It's also for package developers. So if you are a package developer of either an open source tool or a closed source tool, and you want to use, you can fundamentally use Spack similar to how you would use, something like Make in your system. We're not necessarily replacing Make here, but you could use it in your process of development so that Spack will build you up a development environment, and then it'll build you up a development environment, and then you can continue tweaking your application on top of that, bringing in new libraries as you want to test on top of them, or you could swap out, compilers to make sure that your specific application continues to work. We'll see that in the developer workflows tomorrow as well, if folks have questions about that. Spack is a part of the High Performance Software Foundation. This is new as of last year at ISC is when we initially announced HPSF. So it's been going for about a year now. HPSF is a Linux Foundation umbrella project. What does that mean? It really means that Spack and HPSF, they are a neutral legal entity. The project has a technical steering committee of which Greg Becker, who's going to be presenting in just a little bit, is a part of. It allows Spack to be more neutrally owned by many different organizations. And so, yes, the Spack started as a Lawrence Livermore project, and we still contribute a lot to it, but we've had significant, human investment, not necessarily, capital, but like full-time engineers from many other institutions, from Sandia, from Amazon, Google, Microsoft, et cetera. All of these large companies want to help contribute to Spack. And so the High Performance Software Foundation gives us a neutral hub where many different players can come together and work on features and not feel like the lab would ever pull this away from them. Oh, and so Spack started out in 2016. We've got a couple of fun graphs here just showing the growth. And so really, where I was just talking about contributions by other institutions, down here you can see in 2014 to about 2016, when Spack was relatively unreleased, it was just Livermore contributing to it. And so this is, lines of code over time. But right after 2016, after, an SC paper and other folks started getting interested in the project, you can see the contributions have just grown and grown and grown and grown and grown to institutions all over the world. This is not just based in the US. This is not even, Department of Energy. It's truly global where we're getting submissions from. And now you can see if we trace this light blue line all the way up to the top, these are Livermore's contributions. And these are contributions from, everyone else in the ecosystem. And so Spack is truly a global project at this point. Spack helps sustain the HPC software ecosystem via these many different contributors, as I was talking about. By looking at our 2023 data from our documentation page, these are the number of different hits that we got. So the US is still our probably most heavily used, but you can see that we're kind of used all over the world. And then again, we're also seeing that via contributions. So we now have over 8,500 software packages inside of Spack. So this can be everything from those low-level libraries all the way to high-level simulations like ExaWind, that came out of the ECP project, or Emacs or Vim if you're installing a code editor. And those have been contributed by over 1,500 people over time. And Spack is extremely active. We're, for package updates, we're merging, often tens or 20s of updates pretty much every day, and, 100 or so pull requests every week. As I was talking about with HPSF, and Spack's adoption has drawn a lot of attention from both industry and academia. AWS, Google, AMD, they're all supporting the project in one way or another, or contributing, maintaining either their software or other open source software through the project. Intel contributed one API support, allowing us to support the Intel One API compiler, and allows us to build with the proprietary compiler for our build farm so that we can build and test packages so that it's more stable for all of you. As I was just talking about, 1 month of Spack development is pretty busy. This was the lead up to the V023 release last November. And in that month, we merged about 457 pull requests. 126 pull requests were opened in that time that did not get merged. We closed about 61 issues, 38 new issues came up. And, here are our lovely developers. And we had, from those 457 pull requests, we had 142 authors. So that this is really meant to say, all of you that are in this tutorial today, I hope that after going through the tutorial and using Spack for a while, there's no expectation ever that you have to contribute back. But if you want to become a part of the community, we really welcome first-time contributors to, just submit a simple package update, like bump the version, add a new version of the package. That is a great way to get started. That's how I started using Spack back in the day. I was using it to build software, and I just started adding packages. Spack is not the only, HPC AI data science package manager out there. And there are many other good options. Geeks and Nix are more typically functional package managers. They're great for reproducibility. They are a bit harder to parameterize in ways that we often want to in HPC. But there is a large Geeks contingent in especially France, but in the EU. There's a lot of built from source package managers out there. Ones you guys might be most common or most familiar with would be something like Homebrew. Maybe you've used Linux Brew, Macports back in the day, or Gentoo, even further back if you're building your own Linux distribution. Specifically in the HPC space, other ones people might have heard here are EasyBuild, Conda, Mamba, and Pixie. There's also Easy now, which is built on top of EasyBuild, which is kind of a binary distribution. Easy Build is it's a very good build tool for HPC. We'll see a lot of the ways in which Spack differs from Easy Build, but a lot of that can be kind of built around our environments, ecosystems, as well as, kind of making it easier to do binary relocation and support installing from binary like we're going to do in this tutorial. Conda, Mamba, and Pixie are oftentimes ones folks have used here too. Hopefully you'll get a sense through this tutorial of how Spack is a little bit different from them, but Spack very generally extends to lots of different types of open source software where you are mixing both build from source and binary packages, such as the compilers installed on your machine. And especially with some of the changes in licensing around Conda, we know a lot of people are interested in Spack these days, so feel free to ask us questions about that as well. So now let's go grab some Spack VMs. Feel free to reach out if you have questions. I'll be monitoring the chat. If you get stuck or can't log into a VM or something, send us a note. We're happy to help. And then I will hand it over to my co-presenter, Kathleen Shea, to talk about basics here in just a minute.
Thank you for the introduction, Alec. Yes, my name is Kathleen Shea, and we're going to be walking through the basics here. So the first thing we need to do is just clone Spack from GitHub. So in our command line here, we're going to say git clone depth equals 2. That's just to help speed up the cloning a little bit. And we're going to be working off of the -- branch equals releases / version 1.0. First time, very exciting, off of https://github.com/spack/spack.git. And we're just going to place Spack into our home directory here. So ~/spack. Oop, and I misspelled depth. There we go. And now we're going to be working inside of the Spack directory. So cd into Spack. And the next thing that we have to do is source our, or like place Spack in our path. And so we're going to just source our Spack setup script. So since we're in the Spack directory, we can just do source it by saying .share /Spack /setupenv.sh. And there we go. Now Spack is all set up. If we were to run it, then it starts with giving you some helpful commands to start with. So this first one is exactly what we're going to do. Oh, just kidding. Sorry, I was jumping ahead. We also need to update our repo to be our 2025 July version. This is a new part of Spack. And it's to make use of the binary caches later on. So we need to do Spack repo update built in with the tag of version 2025 07.0 for July, our most recent one. And I also typed go. Okay, sorry. So anyway, now we are all good to go with Spack, and we're going to start with Spack list. So if we were to type Spack list, enter, this will show us all the available packages that you can install using Spack. And let's just note that this first time is going to be significantly slower than every consecutive time because the caches are being populated. So bear with us this first time. It'll be faster moving forward. And then with Spack list, you can also use it to take a query string. So if you wanted to look for all Python packages, for example, you can use it as a search to say Spack list and then in quotes py -star, and that's the prefix for all of the Python packages, and you can see all of the available ones there. And this first Spack list is taking even longer too because we have an outstanding 100 people here right now on all of these VMs. So give us a second. Okay, there we go. So as we can see, we have about 8,500 packages available to install inside of Spack, or available to install with Spack. And so your scientific software needs should be pretty adequately covered. And like I said, we could also use it to query. So if we said Spack list py-star to see all the Python ones, first, let's note just how much faster that was. And also that we have over 2,700 Python packages available to install as well. So let's get started with installing a package. So we do this by using the Spack install command. And we're just going to get started with gmake, which is a common implementation of the build tool make. And when we install that, you can see from this output here in the tutorial docs that installed gmake, but also GCC runtime, and glibc. So the glibc and GCC runtime packages are automatically tracked by Spack to manage the consistency requirements among compiler runs, but for the rest of the section, we're going to focus on the packages that were explicitly installed. So for example, the GCC package was found on our system and gmake requires a compiler to be built. So it used that to build gmake from source. And it's already managing some dependencies there with what gmake needed. And like I said, it found GCC, but if you wanted to look at other compilers that were available, you can do Spack compilers or a Spack compiler list. Spack compilers is just an alias for the Spack compiler list. So we can see here that we have 2 versions of GCC and an LLVM. And we'll talk more later about how to configure these and if you wanted to add some in the Spack concept slides and as well as in the configuration tutorial. So we can install software from either source or from a binary cache. And just for the sake of speed, we're going to be using a binary cache today that we've pre-set up. So in order to get that going, we're going to say Spack mirror, add, we're going to call it tutorial, and look in this mirror. And then we also need to trust the keys, but typically this is not the best practice to not check your keys beforehand. So if you are taking a build cache in the future, make sure to check the integrity of it on your own. But for now, for this tutorial, we're going to say Spack build cache keys -- install -- trust. And now we have our build cache. So how we type these install is like our spec syntax. So if we wanted to install zlibng, which is a just commonly used compression library, we can also explicitly ask for direct dependencies using the percentage sign. So for example, that could be a compiler. So let's Spack install zlibng with directly depending on cling. So %cling. And so now we're building a zlibng that was built with cling as a compiler. And this is a separate installation than the first gmake that we did. So now we have both. And the next thing that we can customize with our spec is versions. So if you wanted to have a different version of a package, you could add that. And if you weren't sure of what versions you're looking for, you could do Spack versions, whatever your package is. So let's again go with this zlibng. And we can see the save versions and remote versions. So let's go with this 2.0.7, like an older zlibng. And in order to specify that version, we use the @ symbol. So let's do Spack install zlibng again, but this time with specifying the version that we want, 2.0.7. And so we do @ 2.0.7 and run that. And this spec syntax is recursive, so any syntax we can specify for that root package, we can also use for dependency. So we can do Spack install zlibng, specifying that we directly want GCC to be a dependency of zlibng, or to be built with GCC, and we want that to be at a specific version as well. So once the other zlibng loads, then we will specify also the dependencies version. So Spack install zlibng with the direct dependency on GCC, specifying at version 10. Install. There we go. The next specification you can make for your spec is that Spack also supports compiler flags. So we can specify parameters of compiler flags. And we can do that by just listing the flag that you're looking for equals. And so for this example, we can do Spack install zlibng with that specific version 2.0.7 and also specifying some optimization C flags. So that would be Spack install zlibng at version 2.0.7 with compiler with optimization flags turned on. So C flags equals minus capital O3. Now, in the way that Spack install shows all available packages in Spack, Spack find shows us all of the packages or all of the installations that we've done in our own Spack. So our Spack find query will show us all the things that we've done so far during this tutorial. And that would be just with straight up Spack find. If we wanted to be a little bit more specific and see the flags that were specified, like those compiler flags, and also like the hash of those packages, we can add the parameters LF. But first, let's run through that Spack find and just see that we also have this nice color coding that you can't see in the docs that shows the compilers and the different versions, so we can see those different, all the different installations that we've done so far. And if we added those parameters of Spack find-LF, then we can also see those flags got turned on for that version of zlibng at the 2.0.7 version, and also now we can see the unique hash for each of these installations. And so to get in what these hashes means, we track the provenance of every single installation, meaning everything that makes the installation unique. So then if you wanted to make any change, such as like compiler version, build options, dependencies, those all have a unique hash. So it's easier to follow along and reuse those specific installations that you have. So next, let's move on to another package of Tickle, which is a scripting language. So Spack install TCL. And when we're installing that package, we can start to see that Spack reuses, if there are certain dependencies that it has in common with the package you've already built, then you can see, sorry, I just started my question. It'll not unnecessarily rebuild those dependencies that it has in common. And if it already has a build of that package, it'll just bring that in and help with the building of your next package. So yeah, like you can see here with GCC, glibc, zlib, you know, it's bringing in packages that have already been installed previously. We talked about how to specify a direct dependency, but sometimes we don't really care if it's direct or transitive, or we want it to be applied to everything. And so we can specify that with the caret sigil. And so that would be Spack install TCL with a direct or transitive dependency on zlib ng at 2.0.7. And we're going to directly ask that it's built with Clang, with that % Clang. And what I mean by a transitive dependency too is one that is a dependency of a dependency, like something that's brought in without you explicitly asking for it to be brought in to your build. And going back to those hashes that we were talking about, we can refer to packages on from the command line by their package hash. So earlier when we did Spack find-LF, we saw that the hash for our optimized installation of zlibng began with UMRBKWV. And so instead of typing out that whole spec again and specifying the C flags, we already have an installation of that, so we can just refer to it by that hash. And the only difference here is that if you're referring to a hash rather than a specific, rather than the explicit name, you need to do a / before that. So Spack knows that you're about to give a hash and not a name of a package. So let's do an example of that with Tickle again, that if we want to Spack install Tickle with that zlibng optimized installation, we can just do caret for, again, like the dependency and the / to show that we're using a hash, and YQ5. You don't even need to put the full hash, just enough for it to be uniquely identified. Now, the next thing that our Spack find command could use that's helpful is that it can take a -d flag, which will show dependency information. So if we were to run Spack find -ldf, it would show us the hash, any flags that are turned on, and also some dependency information. So while we're waiting for the, there we go, Spack find -ldf. And we can see that GCC and glibc are dependencies of GCC runtime, and that we have 18 installed packages so far, along with the rest of all of our installations. Now, a little bit of dependency information is lost here. So if there was a package that, if multiple packages in the DAG are have the same dependency, it's only shown one time in the Spack find showing of installations. So it could also be helpful to look at it and visualize it in an alternative way using our Spack graph command. So that's being used Spack graph TCL, just like a more readable one. And you can see the lines of what's connecting all of our packages and their dependencies. So we can see that gmake has multiple, or well, maybe like GCC has multiple dependents is visualized in this graph. And once that loads again on the terminal side, we can see that it has some nice color coding, so you can follow those paths as well. Yes, like this. So you could follow along with all the dependencies in a more visual way. So let's move on to a slightly more complicated package. HDF5 is a good example with an MPI dependency. HDF5 stores and manages large complex data, and if we wanted to look at what the build plan of HDF5 is going to be before we actually install it, we can do that using the spec command. So we could say spec HDF5. And this also really highlights how complicated some dependencies can start getting, and that Spack can, and what Spack's managing behind the scenes for you. And assuming we're happy with this configuration, we can now go and install it. We also have our nice color coding and information in the terminal, as you can see as well. So Spack install HDF5. And see, there's a lot to install. And we can also see again that we're able to pull in other packages that have previously been installed to support future installations. So you can also have different build options for your packages, and we call this variants. So the variants can be specified and enabled using the plus sigil, or if you wanted to disable it, you could use the tilde or minus sigil. So let's install HDF5 again, but this time we don't want an MPI implementation. So we can say Spack install HDF5 tilde for disable MPI. Spack install HDF5 disable using tilde MPI. And so now it's going to do another installation of HDF5, this time without MPI. But you can also enable the MPI again and with a different type of implementation. So if you wanted, in the way that MPI is a virtual package that represents an interface, you can also depend on those abstract interfaces. So if we wanted to have an MPI implementation, but have it depend on a very specific implementation like mpitch, we can do that. And we can also mix these virtual dependencies. So, or sorry, not dependencies. We can mix these virtual packages and these virtual dependencies. So say we wanted to do HDF5, we could use GCC. We could specify that we wanted to use GCC for C and C++ components, and we could specify that we wanted to use the one API for our Fortran components. But for now, we're going to keep it simple and focus on, if we want to do that HDF5 again, and enabling MPI support, and specifically with an MPitch implementation. So let's do Spack install HDF5, enabling high-level API support, shell, and enabling MPI implementation or MPI support. And specifically within that MPI support, we're going to ask that it's the MPitch implementation by using caret MPitch. And we've installed a lot so far, so next we're going to do another check-in on all that we have installed by, again, using this Spack find -ldf for the hash, dependency information, and any flags that are turned on. So Spack find -ldf. And we said we have 69 installed packages right now. And like you said, we did not explicitly ask do 69 different installs. So you can see how many dependencies are being brought in and what Spack's managing for you. All the packages. Okay, so HDF5 was a more complicated example than Zila, Benji, and Tickle, but it's still within the realm of software that an experienced HPC user could expect to manually install, given a bit of time. But let's look at an even more complicated package that could really take a lot of a programmer's time that Spack could reduce. And that is Trilinos, which is a solver tool. And let's just get started with installing it. Spack install Trilinos. And this is where we can really see the power of Spack, because Trilinos can have over 30 direct dependencies, many of which have dependencies on their own, and tracking all of that could take weeks of a programmer's time. And even if that installation could take about 3 hours on a system, that's only 20 seconds of programmer time. So it can significantly save time on managing these dependencies for you. And Spack also manages consistency of the entire DAG. So every MPI dependency will be satisfied by the same configuration of MPI. So if we were to install Trilinos again, specifying a dependency on that previous HDF5 built with MPitch, we could see that then everything that uses MPI in this whole build uses MPitch. And that's done by this line of enabling HDF5 and saying those explicit dependencies that we are looking for again for that implementation. So to do that, we'll say Spack install Trilinos plus HDF5 to enable that support for it for our Trilinos package, and depend on HDF5 with that HDF5 implementation having high-level API support, which is often needed by Trilinos, and enabling MPI support, and we explicitly are requesting that mpitch be the implementation supported for that MBI. And so after that loads and we run spack find-d of Trulinos, we can see that every package in the Trulinos DAG that depends on MPI now uses mpitch. So it is inclusive to the whole installation that you run. And again, Trulinos is such a giant package that it can be hard to parse through all the information in there and seeing all of the mpitch stuff. So this would be a good time again where a Spack graph might be useful, so that you can have different ways of visualizing all those dependencies and seeing that mpitch use as well. So let's start again with spack find-d Trulinos. Oop. Where we can see mpitch is being used, or also Spack graph Trulinos, where we can also see all that dependency information and where mpitch is being used, and just how complicated all these dependencies are. And another way of doing Spack graph is that you could also put it in a dot graph using graphviz's dot format using the -- dot flag. So just to walk, we're not going to look at that PDF yet, but to walk through what that example would be spack graph -- dot Trulinos and pipe that to dot -- PDF and put that into a Trulinos _ graph .pdf file. Okay, so if we were to do just to walk through the example, spack graph -- dot Trulinos, pipe that to dot -- PDF into a file called Trulinos graph .pdf. And that is how you create those diagrams that you've seen earlier on in the tutorial with like the different blocks of the packages pointing around that you'll see later on. So if you're ever wondering how those were made, it is with the dot flag. Okay, so now you're probably, say you use these packages or you don't need all of these different installations anymore. Let's get into how you uninstall packages. So we can do, I'm just gonna stop this. Oh. Okay, just kidding. It's not stopping. But if we do spack find -d and tickle, we can see those different tickles that we installed, the 3 different installed packages, 3 different installations of tickle that we did throughout this tutorial so far. So spack find -d tickle. There they all are. We can see how like this one has a different version of zlibng than these ones. All of that's still tracked and maintained. Or if we wanted to find all the versions of zlibng that we've done throughout the tutorial, let's find zlib-spack find zlib-ng. And there they all are again. And we can just uninstall packages by spec using the same syntax as install. So spack uninstall zlibng And let's say we don't want that version with GCC 10 anymore. So we're going to say, let's uninstall the one with the direct dependency with that percentage sign on GCC version @10. And it's going to ask you if you're sure you want it to be uninstalled, and if you would like to proceed, we're going to say yes. If you already know that ahead of time, you can include that -y flag in your uninstall line. And now when we look again for all of our zlibngs by doing spack find -lf zlibng, we can see that we went from 5 installed packages to 4, and that specific one that we had with GCC 10 is now gone. We can also uninstall packages by referring only to their hash. So if we wanted to do spack uninstall zlibng that had that OpenMPI version or OpenMPI support, then we could do the BZI hash. Again, making sure that we use that slash to tell Spack that we're using a hash and not a package name. And, oh no, we got an error, but that's good and to be expected because Spack is warning us that there are still dependents of that package. And if you uninstalled that, then all the dependents, like those installations wouldn't work anymore. So if you really do want to do that, you can use the -s force command, but likely you want those dependents to be gone as well. And so you can specify that when you're doing the uninstall. So you could say spack uninstall. Yes, I'm sure I want to do this. -- dependents to make sure those dependents are uninstalled as well. And again, put that zlibng with our OpenMPI implementation, or with the one with OpenMPI support for MPI, and that was with BZI. So now, not only is that zlibng got uninstalled, but also its dependent of tickle was also uninstalled. And Spack will also not uninstall packages that aren't sufficiently specified. So if we tried to do spack uninstall Trilinos, it would say we have multiple Trilinoses. You're going to have to be more specific about which one you want to be gone. If you did want all of the packages matching an ambiguous spec, like I don't want Trilinos at all anymore, you can use -a or -- but we probably just, in this example, we're just going to say that we want a specific Trilinos uninstalled. So we say spack uninstall, and we're going to use this hash again. We want the OpenMPI one to be uninstalled. So we'll say spack uninstall / to say that we're referring to a hash 5AG. And yes, I would like it to be uninstalled. And there we go. Now it was successfully uninstalled. So let's get into some advanced Spack find usage. So we talked about, or Spack find commands will accept what we call anonymous specs, and those are expressions that do not contain a package name. So for example, we've had multiple packages that use mpitch support, and we could find all of those packages that have that. So we could say spack find caret all the packages that depend on mpitch, either directly or transitively, mpitch. And we can see that Trilinos uses it, and so does HDF5, if we recall earlier in the tutorial. Or you could also do this for all the packages, all of your installations that have those optimization flags on. So we could also do spack find C flags equals -O3. And we can see that zlibng is the one that had our optimization flags turned on with this specified version. The find command can also show which packages were installed explicitly rather than pulled in as a dependency using the lowercase -x. And if you wanted to see all of the packages that were pulled in implicitly, then you can use the -X. And we also support the -p flag to show paths in the find. So if we did Spack find dash, oh my goodness, I always do a space after that. Spack find dash px, then we can see all of the packages that we explicitly installed and their paths. So we can see all those things that we did with our zlibs, trulinos, hdf5s, and what their path, their coinciding path is. Now let's get into customizing compilers. So again, we did this a little bit earlier, but again, if we did Spack compiler list or the alias Spack compilers, we can see all of the compilers that Spack is currently aware of. And these compilers are maintained in a YAML file. Later on in the tutorial, we'll discuss how to configure external compilers by hand for special cases, but we can also use Spack to install specific versions of compilers that we want to be able to use. So for example, we have these two versions of GCC, but say we wanted GCC version 12. We could say Spack install GCC at 12. And once that's done running, we run Spack compilers again, we can see that that was added and that we now have GCC version 12 to be able to use for our installations. And since GCC 12 is a newer version than the other external compilers that Spack already knew about, this will become the default compiler since it's the newest one. And we'll discuss how to change these defaults in a later section, but for now, since it's the latest, since it's the most recent, the newest version of GCC, that does become the default. So once this finishes running, we'll again do a sanity check that we're matching the documentation and that the new compiler is there. So Spack compilers. And yep, there it is. And it's also different than like externally found, like we can see that we specifically did add it. And for the rest of the tutorial, uh, we'll sometimes use this new compiler, but we'll sometimes want to demonstrate things without it. And so if you've gotten lost or whatever, this is still, it's probably one of the more important things to do for the rest of the tutorial to run smoothly in the next sections. So we'll make sure to uninstall that GCC version 12. So make sure you do Spack uninstall GCC version at 12. And yes, for sure we want to do that. Oh, yes. And if we did Spack list compilers, oh, oops, Spack compilers, we can see that now it is no longer there. And that's all for the basics, and Greg is going to tie that into some greater concepts. Thanks so much, guys.
All right. So now that we've done a little bit of working with Spack and maybe have a little more framework to hang these concepts from, we're going to go back. This is going to be our last bit of slides actually for the entire tutorial. But we're going to go back and do some core concepts in Spack, and hopefully that will provide a framework that will make the rest of the hands-on after this a little easier to fit into kind of where it fits in what we're doing. So the big point of Spack, and I think Alec mentioned some about this earlier in the intro, is that Spack supports combinatorial versioning. So looking at the overall ecosystem of package managers, this is a little unusual. Traditional binary package managers are not for that. They're for getting a single managed stack. It's going to be very stable, it's going to be very well tested, but it might not have exactly the combination you want. And that's just the trade-off. Things like port systems allow a little bit more parameterization, but generally just by compilers and dependency versions, And then virtual machines and containers obviously give you all of the freedom in the world, but at a certain point, then the question becomes, how do you build the things that go in the container or the virtual machine? And you're right back where you started. So Spack provides a syntax for talking about this combinatorial space. And we've seen this in the basic section that Kathleen talked about, right? Spack install MPI leaks is an unconstrained Spack. Spack will install whatever its default for MPI leaks is. MPI leaks, by the way, is an MPI memory in a tool for debugging MPI memory leaks or message leaks, developed at Livermore and therefore familiar to the people who wrote the tutorial. So you'll see it come up a few times. If we say at 3.3, right, that's the version. The percent for a direct dependency, and the version obviously telescoping into the dependency. So, right, what we can say about MPI leaks, we can say about GCC and specifying its version. We can specify build options, compiler flags, architectures, and again, with the caret, we can specify dependencies more broadly, whether it's a direct dependency or not. The Spack packages are also parameterized. So for every package in Spack, there is one package.py file. And that is an important distinction for understanding this, because where other packaging systems might have a recipe for building Kripke on X architecture or with X compiler, Spack has one recipe that is fully parameterized by all of the options that go into building. So generally, we can think of the package file as split between the install logic at the bottom and the build metadata at the top. And the metadata effectively describes what is the possible space of builds of this package. And the build recipe then takes as an argument a spec, which is a concrete spec, which points to a single point in the space of all possible builds. And this resolves some of the difficulties that you may have faced if you write CMake or AutoTools packages, where a lot of the complexity in writing a build system goes into detecting what's on the system and figuring out what you actually are building. Where is the dependency? Which dependencies are available? All of that. With a Spack package, all of that is handled at concretization time, and at install time, you know exactly what you're building already. The DSL for specifying this dependency metadata or other aspects of the metadata, variants, versions, the space of possible builds. This language has a lot of expressive power, particularly because just about everything, except for versions, can be conditioned by a when clause. So you can have a dependency conditioned on a variant, you can have a variant conditioned on another variant, you can have a dependency conditioned on an architecture, all these sorts of things that describe the real world of package management. From the command line, we've already seen this in the basics section, specs can constrain versions or other attributes of their dependencies. And Spack ensures one configuration of each library per dependency graph. That's a directed acyclic graph. We'll refer to those a lot. And you don't have to know anything about the structure to be able to say on the command line, I want to change how the libelf node is being built. And then Spack for link and run dependencies will absolutely guarantee there's only one version of them in the DAG. And for build dependencies, it will try to keep you to one, like compilers. It will try to keep you to one compiler. But if you specify that you want this node built with GCC and this one built with Intel, Spack will say, okay, you asked for it, you got it. We've talked about virtual packages already. But a package, if we think back to the package.py file that we saw earlier as an example, you wouldn't say that depends on mvapich2. You would say that depends on MPI. And then at concretization time, Spack will figure out either the default one, or if you asked on the command line for mvapich or for OpenMPI, which one to fill in. And these versions are interfaced. Generally, you wouldn't use it from the command line, but in packages, you can say depends on MPI at 2. So I've used the word concretization, I think, already, but we should talk in a little more detail about what that means. The user input is an abstract spec with some level of detail about what you want installed. And you can think about it as normalizing and concretizing, but it's all one algorithm that's going to take that abstract spec and it's going to turn it into a concrete spec with all of the decisions made. So this involves applying defaults, resolving constraints, all of that, and then we store off that metadata. It came up in the chat earlier about the DAG hash. Every DAG, every bit of the provenance of the spec that goes into the DAG and the package.py file is then hashed, and every node in the DAG has a hash. This is obviously this is what allows us to install all of these combinatorially different packages in the same file system, obviously. It also does lead to some complexity in terms of finding dependencies. So Spack embeds RPaths in all of the binaries. Things will work the way you built them. You don't need to remember at runtime to load the particular modules that are compatible with how you built the package or any of that stuff, which is sometimes a feature of dealing with HPC systems. With Spack, it will find it through the RPaths, and the assumption is that at build time you knew how you wanted it built. We run the compilers in an isolated environment. I'm not going to spend too much time on this, but it is a relevant part of our process. We fork a process for every installation and sanitize the environment in that process. You can configure Spack to build with external software. Peter is going to talk about this more in the last section of today in configuration. But when you concretize to an external spec, we just prune the DAG right there. We don't know anything about the dependencies under that external spec, but what we do know is where it came from. And so that's the provenance that you get for an external. Spack comes with a built-in package repository, but you can add I see a question about RPath. Spack will run with the true RPath, the older one, which is not overridden by LD library path by default, but you can configure it to use runpath instead, if you prefer. So Spack allows you to extend the package ecosystem with your own package repositories. So here's a graph of Marble, which is a Livermore multiphysics application. And you can see here's obviously a scaled down version of the graph, but with the packages in different repos. So if you configure a repository, you can have new packages in it. You can also have copies. You can have implementations of existing packages that inherit from the built-in and tweak or add small bits of behavior without having to maintain the entire package yourself. And these repositories layer, as you can see in the example. Spack also allows you to define mirrors. A mirror is a directory with directory or other source with local information on either the source or binaries available in Spack. So in the basics section of the tutorial, we configured a mirror and we didn't talk about it too much. We'll talk a lot more about mirrors tomorrow. By default, Spack maintains a mirror of everything you've fetched so far, called the download cache. You can also host local mirrors, say in your shared file system. That's useful if you have an air-gapped system or the internet is not accessible from the compute nodes of your system that you're building on or anything like that. We have the global Spack mirror, which is a mirror of everything in Spack. It tends to lag a little bit behind, so it's a mirror of most of everything in Spack that lives in S3. And you can also have mirrors in OCI registries. And then only if the resource that you're looking for is not found in any of your configured mirrors, then Spack will go out to the original source on the internet to download it. The concretizer has to synthesize a lot of different sources of information coming from a lot of different places. There's all of the metadata information about the possible space of builds for a package from the repository. We talked about that in the package.py's or package.py files. There's the abstract spec, the command line constraints that the user has put in, and there's all of the config options, which Peter will talk about more later, that can also affect concretization. And on top of that, dependency resolution is an NP-complete problem. So the quote new concretizer in Spack, which has been around in various forms for quite a while now, is implemented in answer set programming. Clingo is the specific ASP solver that we use. And ASP is a logical programming language, looks kind of like Prolog, but has the additional benefit of being guaranteed to terminate. And the program has two parts. There's a small program that is the solver, and there's a lot of generated facts that we emit at solve time that are then resolved by Clingo into a single spec. And the big win about this for us initially was the full backtracking. It resolved a lot of issues at the time, but it's also allowed us to add a lot of new features that we simply couldn't have implemented before. So the original default mode of Spack, which you can now access through the --fresh option, resolves all the metadata for the packages the way I described earlier, and creates a hash for each thing, and then looks whether it's already there, either as a binary package or already installed. And if it's an exact match, it'll use it. But with reuse, we can tell the solver, hey, these are the things that are available already. And if it's not a violation of the constraints to use one of them, please do so, because then we don't have to wait around for it to build for quite as long. So we use the hash as the ID for the package, as always. And something like minimizing builds is pretty simple. If you have a node, you can apply a hash for it. If you choose a hash, you have to impose all of the constraints from that hash. A build is something that you didn't pick a hash for, and we'd like to minimize builds. And in the first implementation of this feature, it really didn't look that much more complicated than that. This allows us a huge benefit in the amount of packages that we reuse, but it does mean that you have to exhibit a little bit of care to make sure if you're seeing an unusual concretization, are you seeing it because there's a bug, or are you seeing it because Spack is choosing the things you already had installed, but you decided you didn't want those things? So in some cases, you'll want to turn off reuse or uninstall the things that you're reusing that you don't want. We talked about the Spack spec command in the basics section. This is incredibly useful to see the results of concretization. It's also, if you keep needing to resolve the same spec over and over again, and you're waiting for the concretizer again and again, the Spack spec command has options for YAML and JSON format that you can output the concrete spec and pass it in from a file as a concrete spec to the next command to speed yourself along your way. Now, the last thing that we're going to talk about in the concept section are Spack environments. And Spack environments work kind of like Python virtual envs, if you've used those, or a lot of other sorts of manifest and lock file environments in other package managers. But basically, it extends the idea of an abstract and a concrete syntax, which we already have with abstract and concrete specs, to files describing a collection of specs. So a spack.yaml file fundamentally is a list of specs that you want to install and some config to use while you're dealing with those specs. And the spack.lock file describes exactly the concrete specs that Spack picked from those. So you can concretize the environment, look at whether you got what you wanted, maybe change the environment, reconcretize it if you're not happy with it, and then install those packages. The Spack environment is also the underlying machinery behind a lot of advanced Spack features. So Caetano is going to talk next about Spack environments, and then tomorrow I'm going to give another section on what we call Spack stacks, but basically large combinatorial deployments with Spack. That's going to be based on environments. We're going to have another section tomorrow on developer workflows. That's going to be based on environments. We're going to have a section on binary caches. That's going to be based on environments. So it really becomes kind of the core machinery behind a lot of what we do with Spack.
So in this section of the tutorial, we're going to be talking about Spack environments, which essentially allow you to install collections of packages in an isolated manner. You might want to do this if you are managing software requirements for different projects, if you are deploying certain software stacks to your users, or you just like to maintain different collections of Spack package installations and keep them isolated from each other. So as Greg mentioned in the concepts section of the tutorial, there are two files that make up a Spack environment. There is the spack.yaml file, which contains the packages you would like to have installed within the environment, the compilers to use to build those packages, and other Spack settings that define how your environment will be concretized and how the packages will be installed. You can think of the spack.yaml file as sort of the abstract representation of your environment, like you would think of an abstract spec, for example. The spack.log file is a file that is generated by Spack when your environment is concretized and represents the complete provenance of your environment, which will enable the reproducibility of your Spack environment either across different machines or on the same machine, but potentially for other users. So we're going to talk about the use cases of environments, and as Greg mentioned, they sort of form the building block of a lot of other advanced Spack features. So I mentioned that there are many ways to use environments. You might like I said, have environments be used for different software projects you're on. If you'd like to document a software stack and have that be reproducible for other users to be able to share your environment in a version control system like Git, or use them for things like a CI/CD pipeline where you need to constantly generate new builds of your environment, either for testing a specific software package or just performing any other type of evaluation that might be helpful to have be done within a Spack environment. So let's get started with the basics of a Spack environment. So at this point in the tutorial, if we run Spack find, which will output the currently installed packages within your Spack instance, you'll see we have 76 packages installed, but this list is quite cluttered, right? I mean, you have all these versions of zlibng, you have multiple installations of HDF5, all sort of segmented by the different compilers that were used to build them, which isn't exactly, if you're managing different software projects, it's not exactly helpful to see this cluttered list. That might not really help you decide or manage the current project that you'd like to be isolated in. So that's sort of what the idea, the motivator behind why you might want to use a Spack environment. So to create a Spack environment, you can use the spack env create command. So we're going to create an environment called my project. So let's run spack env create my project. You'll see that this generated a environment called my project. It placed those files inside the var spack environments subdirectory within your Spack instance, and it gives you a message that you can activate it with this command. So you can see a list of all the environments you've created so far by running spack env list. And as you'll see, we have the my project environment listed here. So once we've created the environment and verified that it's been created by using the spack env list command, we can activate the environment by running spack env activate my project. There is a shorthand alias for this, so you can run spacktivate, or when you are, deactivating the environment, there's also despacktivate. So those sort of aliases will help you, make that workflow a little bit easier if you're switching in and out of environments quickly. So once we're in the environment and we run spack find again, you'll see that there's no longer this huge cluttered list of packages that we previously saw in our invocation of spack find. So this is because we have this isolated environment. We have not installed any specs in this environment yet, so you're not going to see any output here. And you'll see that because we haven't really done anything in the environment yet, there's no concretized packages to install. There's nothing here. So once we verified that this environment is empty, we're within the environment, the spack find command will give you that output. But at any other time, if you want to verify whether or not you're in an environment, you can always run the spack env status command, and it will tell you which environment you're in. And like I said, you can either use despacktivate or spack env deactivate to leave your environment. So I'm going to use spack env deactivate to leave the environment, and we can immediately verify the status by running spack env status to show we're no longer in the my project environment. And when we run spack find again, we come up with this entire list of cluttered installations that we have within our Spack instance. So now we want to get to actually installing packages within an environment. Let's first get back into our my project environment by running spack env activate. And then let's try to install the Tickle scripting language. So using our previous knowledge of Spack, let's try to use Spack install Tickle. So Spack will immediately complain because you cannot use the Spack install command vanilla to add packages to your environment. The reason for this is that Spack environments are sort of set up to be collaborative, and you might be sharing these environment files across multiple systems with different users, and having a safeguard that prevents you from sort of easily destructing or adding things to the environment without sort of explicit need or intent can sort of that adds a safeguard to prevent sort of this destructive behavior from potentially happening. So you have to use an explicit command to add tickle to the Spack environment. So we're going to use Spack add tickle, and then you'll see that tickle is now in our environment. It is not installed, but it is essentially registered as a root spec, a concept that I'll get to in just a second. So let's say we also wanted to install an HPC solver into our environment. We will run Spack add Trilinos, and that is now in our environment. And now when you run Spack find again, you'll see that we have our two root specs in our environment. They are not installed, which you can tell because there is a minus sign here. And root specs essentially are the packages that we want to explicitly request to install within our environment. They're not dependencies, and they sit at the top of our dependency graph. So now that we have two of our packages in sort of added to our Spack environment here, our environment my project, we can install them. So running Spack install without any additional arguments will first concretize tickle and Trilinos using the default settings that we have in our environment, which we will get to in just a second. It will concretize those packages and it will install them. So when we get the output of the installation here, you'll see that a lot of these packages were already found within our Spack instance, which is the default behavior of environments that we try to reuse as many existing installations as possible in order to save time and effort. But this is a setting that you can configure and will be talked about in the next section of the tutorial. So once this is finished concretizing, when we run Spack find, you'll see that you no longer have those two minus symbols next to the specs in your environment. You have the plus symbols, and you also will have a list of all the dependencies segmented by the architecture of those installations and the compiler that they were built with. So you'll see that the specs concretized, they are installing, and it's finally installing the last package here, Trilinos, and everything successfully was built and installed. So you'll see the last line here says that the view was updated for the My Project environment. So this is an essential feature of environments. So someone asked previously, how can you install a package and have it added to your path? So the beauty of an environment is you can, if you have environment views enabled, which they are by default, your root specs will automatically be loaded into environment variables like path and man path and other equivalent environment variables that essentially emulate as if that package was natively installed on your operating system. So an environment view essentially creates a symlink from the installation of that package to bin paths, user paths, library paths, man paths underneath that view. And as we'll see later, they automatically get added to those environment variables. But we can demonstrate that actually works by verifying that Tickle is actually installed within our environment and is available in our path automatically without needing to do any extra loading. So if you run which Tickle sh, you'll see that Tickle sh is within our environment view. It had been Tickle sh, and we can verify that it works here by running Tickle sh. It's in our path, and then running hello world just to show you that everything is working well. Hello world, and then that printed, and now we can exit. So we've installed packages into our environment, but what if you wanted to remove something from our environment? Let's say you have a scenario where you have your first environment that we created, we had Tickle and Trillinos in there. But let's say you had a different software project, you wanted to isolate your Spack installations in that environment because you have different requirements for that specific project. Let's say you had Trillinos at a time, but you no longer required it. So let's create that second environment just to demonstrate what would happen and to show the isolation that Spack provides when you're using this environments feature. So let's run Spack env create my project 2. And then we will activate the environment by running Spack env activate my project 2. And let's add 2 specs here. So we'll run Spack add, SCR, and Trillinos. SCR is a checkpointing library for HPC codes, and Trillinos we're already familiar with. So we will run Spack install. And just to remind you of the scenario here, we're assuming that we will have created 2 environments, right? Trillinos and Tickle in the first one, and SCR and Trillinos in the second one. The scenario is that we no longer need Trillinos in our second environment. And along with the assumption that because Spack tries to reuse as many installations as possible across environments, it's possible, and it's true in this case, that the Trillinos hash will be the same in the first environment and the second environment, meaning that they're essentially pointing to the same installation. What we want to test is that when we remove a package, when we remove the Trillinos spec, the root spec from the second environment, what will happen to the first one? Will that be affected? So we're just waiting now for the for SCR and Trillinos to concretize and to install, but it should just be a few extra moments here. So once that's done, we'll be able to demonstrate our use case here. So this is finishing up here, and it's great that we have the binary cache here, or else this would be taking a lot of time. So just about done here. And SCR is getting installed, and we'll verify that the My Project 2 environment will have the 2 root specs installed, SCR and Trillinos. So we'll run Spack find, and we have 81 installed packages here, and we have our 2 root specs, SCR and Trillinos, along with all their dependencies. And you'll note here that when you run Spack find within an environment, the bolded specs are the root specs when you are looking at this entire listing of the installed packages within the environment. So like I mentioned, we now have these 2 environments with different package combinations, but that common root spec Trillinos. So what happens when we're within the My Project 2 environment and we try to uninstall Trillinos? So let's run Spack uninstall with the Y flag to prevent any prompting, Trillinos. So Spack will immediately refuse to uninstall the Trillinos spec because it's referenced in another project. So this is sort of pointing back to those safeguards that I was mentioning before. We don't want it to be easy for someone to destructively act within a Spack environment to potentially cause these downstream effects on users in other environments or otherwise in the Spack instance. So we need to be explicit about about the actions that we would like to take within an environment. So we can verify that nothing happened within the My Project 2 environment by running Spack find, and you'll see that SCR and Trilinos are still here. The correct action to take would be to run Spack remove Trilinos, which will remove the reference of Trilinos as a root spec from the My Project 2 environment. And let's run Spack find again. And you'll see that Trilinos is still referenced in the entire package installation because the output of Spack find is also dependent on the concretized manifest of the environment. So we'll need to run Spack concretize again we need to run Spack concretize in order to update the listing of packages. Spack concretize. And you'll see that the view is getting updated. And when we run Spack find again, you'll see that there are no references to Trilinos or its dependencies. So that worked well. And as you can see in the previous output, they were grayed out. So let's verify that the My Project environment was not affected by these actions. We'll go back to the My Project environment by running Spack env activate My Project, running Spack find, and seeing that Trilinos was not affected by the actions we took in My Project 2. So this demonstrates the isolation of environments and that those safeguards preventing either you or another person interacting with the environment it's not so easy to sort of have a negative impact on your Spack installation because they're isolated well. So let's take a look at the configuration of an environment. The spack.yaml file, like I mentioned, is sort of the abstract representation of your environment. It contains a list of the root specs you've added to the environment, and it also contains configuration defaults that we'll explain in just a bit. And it can be extended in a way that can make your environments combinatorial. And like I mentioned, this configurability of environments allows you to leverage other Spack features that are more advanced. So let's take a quick look at the spack.yaml file. We're gonna do a quick terminal hack here by running editor equals cat spack config edit, which will print the output of the file that spack config edit is pointing to. And you'll see here that within the My Project environment, we have our two root specs here. We have Tickle and Trilinos. We have views automatically enabled, and we have this unify feature enabled for the concretizer, which will enable that behavior that I mentioned before, that Spack will try to reuse as many existing installations as possible. So when we potentially install Trilinos in another environment, it will try to pick up that exact version if there are no constraints preventing it from reusing that installation. So we've talked a bit about these configuration details, and if you're interested in the more advanced information about configuring your environment, like I mentioned before, there's going to be a configuration section of this tutorial right after this section, and the Spack documentation is more comprehensive in detailing what you can do with it. So let's actually edit the Spack environment configuration to show that you can not only edit your environment by using Spack add and Spack remove, but you can also just add constraints directly by editing your environment. So let's say we wanted to require mpitch as the default MPI provider using Spack config edit. We want Tickle and Trilinos if they depend on MPI at some level to use mpitch as the MPI provider, rather than letting the Spack concretizer decide those defaults on their own. So let's run spack config edit, which will open your spack.yaml file within your activated environment in the default editor. So if you would like to use a different editor like Emacs, be sure to set your editor environment variable before running spack config edit. So now we are within this configuration file, and let's add a section to this packages configuration option here by typing packages, MPI, pointing to the MPI virtual, and then requiring mpitch as the provider for MPI throughout this entire environment. So now we've made those changes, and because we've made modifications to how either dependencies can be resolved or the root specs themselves can be resolved, we need to reconcretize the environment. Because, obviously, because we made these changes to the MPI provider constraint, the current state of the environment is out of sync. So we need to do that concretization. So let's run spack concretize force, which, as you'll see when we see the full concretization output, Trillinos will now use mpitch as its MPI provider, rather than picking up what the Spack concretizer decided by default in our previous concretizations of Trillinos. And we won't be installing the resulting concretized state of the environment, but you can if you would like to. But essentially, once this concretization is successful, you'll see that you can add additional constraints to your environment by simply editing your environment configuration and having the knowledge of this Spack concretize command will be helpful if you are incrementally changing your environment, or just sort of having to play around with the different requirements you may have on your system and how you'd like those packages to be installed. So now we have our concretized root specs here. The graph isn't really showing itself that well because the text size is quite big, but you see that, let's see, mpitch is in here somewhere. So what we did before, when we created environments, was we essentially added root specs and then we concretized them, right? But what if you didn't know what root specs you wanted to have installed in your environment, and you're potentially wanting to, what we call, create your environment incrementally? So an example of this would be you create a fresh environment and you know that you want Python. So you add Python and you install it. But then let's say you want to add a spec of, you want NumPy at a specific version. So we're going to see what the benefits of this approach are and what the drawbacks might be compared to the previous approach of adding your packages, adding your root specs to your environment configuration, and then concretizing those together. So we are going to temporarily create a new environment by using the temp flag in the spack env activate command. So let's run spack env activate, and then temp. This will create and activate the environment all in one go. And let's use the spack install command with the add flag, which will add that spec to your environment and install it at the same time. So this is an alternative to running spack add and then spack install. So let's run spack install with the add flag and then Python. This will concretize and then install a recent version of Python. But let's say you have this installed, you're using Python for whatever reason in your project, and then you decide that you need NumPy at this specific version of I think 1.2.0. And you can see, what you might anticipate what sort of problems might pop up if you're installing a recent version of Python and the subsequent software that you'd like to install may have a different constraint. And part of like what this example is trying to show is that when you are installing, when you're creating an environment incrementally, the Spack concretizer will act in a greedy way, meaning that it will, for example, if we are, if we have the latest version of Python and then we have a spec that requires Python, but and then the concretizer will basically look for whatever version of Python is in the environment and decide, okay, this is what we're going to use. But as you'll see in a second, that's not always how it'll work out. So let's install NumPy at the specific version by running spack install with the add flag pi numpy at 1.20. So we should be getting an error message here in just a second after the concretizer failed to perform its work because it attempted to do this greedy concretization where it would try to concretize this version of NumPy with, or would try to resolve an installation of NumPy with the already existing Python version within the environment. So as you can see, the version of Python available within the environment is not compatible with PyNumPy. And this is a problem that you see when you attempt to create an environment incrementally. And something you wouldn't see if you created this environment all at once. You added those two root specs. And then as you'll see, when we reconcretize this environment like we did before, it will actually resolve the true what the version of Python that NumPy actually needs to be successfully installed. So to do this, we'll need to add NumPy into our environment by running spack add pi numpy at 1.20. That we need to do this because the previous command line invocation failed. So now we'll run spack concretize with the force flag, which will try to find the Python version that is compatible with this version of NumPy that we would like to install. And like we saw before, it's not compatible with the already installed version of Python that we have in the environment. It's going to find a less recent version of it. So you'll see that this works. And there are essentially two other advantages to concretizing your environment all at the same time, rather than doing this incremental approach. If you have, a number of specs that can be installed together, adding them first and then installing them all at the same time, like we did with SCR and Trillinos and like we did with Tickle and Trillinos, that will share as many dependencies as possible and it will reduce the total installation time. Like we saw with this example, we unnecessarily installed a version of Python that is not useful to us because our NumPy version requires a lower version of Python, right? So that sort of added some extra time and is taking up more disk space, etc. Another advantage to installing your packages all at the same time is you can take advantage of Spack's install level build parallelism, which not only means that Spack will attempt to build packages with multiple make jobs at the same time, but it will recently in 1.0 we've added a feature where multiple packages can be built at the same time, taking advantage of the parallelism on your system. So Kathleen implemented that, and it's helping to speed up our installations here within environments and other aspects of Spack. So let's say you wanted to use the programs that we've installed within an environment. We've already demonstrated that Tickle was automatically loaded into our path when we activated our environment. and had it already installed within the environment. But what if we wanted to build software using libraries that we've installed? So let's activate our My Project 2 environment by running spack env activate My Project 2. And then we will run spack env status to verify that we're actually in the activated environment. And we'll verify that we have an MPI compiler here by running which MPI-cc, and you'll see it's available in our view here. So like I mentioned before, a view essentially emulates, as if, the software that you're interested in your environment, is sort of natively installed on your operating system, because Spack will automatically add the environment view to its respective, environment variables, which you can see here by running env and then grepping path equals. So you'll see that it's added to the package config path, the man path, CMake prefix path, Python path, etc. So this will enable you to not only use the software within your environment on the command line, but also on a number of other software installations and contexts. So let's demonstrate the use of these environment variables by building a really simple MPI program that will use some of the libraries that are installed within our Spack environment here. So let's create a program called mpi-hello.c. So you can open up an editor here, and then I'm going to use Vim, so vi mpi-hello.c. And then I'm just going to walk through the source code here. So we're going to include the MPI header, we're going to include the header for zlib, and then essentially what this program does, it's going to print a hello world from each MPI rank, and then on the first MPI rank, it's going to print the version of zlib and zlibng that was found when it included that header. So let's close the source here, and let's compile the program. So MPI-cc, when it's run, it will automatically include the header to the MPI that it points to. So we can run MPI-cc and then point it to the source code file. And then using the spack location command, we will use that to find the location of zlibng and then point it to the path of its headers. So we will invoke spack location with the I flag, zlibng, and then the include subdirectory. So that will output a.out as the executable, and we can run that with 2 MPI ranks. So MPI run, then n2, which specifies the number of ranks, and then point it to our executable. So we get our hello worlds from both of our MPI ranks, and we see the output of the zlib and zlibng versions. So we want to verify whether or not, including that header actually pointed to what's available in the installation, right? So we can run spack find and then provide zlibng as the argument in order to see what version of zlibng is actually within this environment. And as you can see, it matches exactly what was output by our program, showing that the headers are from within our environment, from the instance of zlibng in our environment. So to the last component of this section of the tutorial of Spack environments, let's talk about how they can be leveraged to reproduce builds across many different contexts. So Spack environments provide users with these virtual environments, these isolated environments that are similar to a Python virtual environment or a Conda environment. We've talked a bit about how they can be leveraged as not only a way to list the packages that you would like to be installed within a specific environment, but they can also be used to specify the configuration of how that software is installed, additional constraints either to your compiler, to different providers like MPI, or to different virtuals like MPI, and the providers that you would like to use to actually install, and also how those packages within your environment are concretized. So we've talked a bit about, Spack.yaml as sort of the abstract representation of our environment, and as Spack.lock storing the provenance of our environment. And we'll demonstrate how both of those files are used to reproduce environments at different granularities, essentially. And I'd just like to point out that both of these environment files can be versioned in dependencies and shared with different people and used to install the same set of software by different users and on other machines. So you can take either of the environments we've created today and share those with different people, and they will get, they will be able to install that software on their machine to the preferences that you set, essentially. So there are two types of Spack environments. We've mostly been dealing with a managed environment, which are created when we run Spack env create. And like we saw before, these are automatically created in the var Spack environment subdirectory within our Spack instance. And an important distinction is that they can be referenced by their names. There's also an independent environment that essentially points to any directory outside of that var Spack environments directory. And they can be created by using the Spack env create d with a d flag and then specifying the directory. Or you can, essentially just have a folder with spack.lock and spack.yaml and have that be a directory that can be activated by Spack. But independent directories are not named. They're not explicitly, managed by Spack. So, which it can be useful depending on the sort of reproducibility or the sharing that you would like to do with your environments. So just to review what's actually in a managed environment, let's change into the directory of our environment by using the spack cd command with the E flag representing environments, and then we will change into my project. So spack cd E my project. So you'll see now that we're within our var Spack environment subdirectory, and we are now here within my project. So if you run pwd, which gets the present working directory, you'll see what I have on the prompt as well, if you would just like a new line there to demonstrate where we are. And if we list the files available within this directory, we have spack.lock, which is the complete provenance of our environment. It's a concretized version of our spack.yaml configuration file, which we edited before. And if you run spack env list, you'll see that my project is a, it is a managed environment because it is named and because it is listed when you run spack env list. So we previously edited the spack.yaml file, and we can demonstrate here that it's the same thing that we edited when we added this constraint on requiring mpitch as our MPI provider and our root specs here, in addition to our configuration options that were set by default. So let's create an independent environment. So let's change back into our home directory, and let's make a directory called code. Change into that directory code, and then let's create a Spack environment, an independent Spack environment by running spack env create with the D flag, and then referencing the environment, or sorry, the directory that we are currently in. So Spack will create that independent environment, and it'll tell you that you can activate it with spack env activate. When we list what's in this environment, you'll see that we have a spack.yaml file. There's no spack.lock because we haven't concretized anything in this environment yet. And if we run cat spack.yaml, you'll see that we have no root specs and we have our default settings here. And if we run spack env list, this new environment is not referenced. So let's add some specs into this environment. So we will open spack.yaml in our text editor. I'm going to use vi spack.yaml, and let's add a couple specs here. So I'm going to add Trilinos, and open MPI. And close the editor here. And now we're going to activate the environment because as you can see here, when we run spack env list, the my project 2 environment is still activated. So we can reference a directory that is an independent environment when we run spack env activate. So spack env activate and then dot. And then we can run spack install, which we've done before. So that'll concretize those two specs and it will install them within our environment. So, this will behave exactly like we saw with a managed environment. It'll update the view, which, as you can see, will be present in the environment, the independent environments directory itself. And because essentially what is within a Spack environment view is symlinked to installations managed by the Spack instance, you'll see that those links are essentially just added to the view if you wanted to go in and sort of investigate what's within this directory code.spackenv/view. So once this concretization is done and once those packages are installed, we're going to talk about how to when to use the spack add command and whether or not that's interchangeable with simply just editing spack.yaml directly. So you'll see that everything's installed here, the view is updated, and let's say at this point we want to add HDF5 to our environment here. So let's run spack add HDF5 and then at 5.5.1. It successfully worked. And then when you run cat spack.yaml, HDF5 with this constraint was added as a root spec. So you can either, if you wanted to add additional constraints to this HDF5 spec, or if you wanted to remove it, you could simply, vi spack.yaml, or you could just use spack remove HDF5, which will work automatically because there is no other spec that there's no other root spec within your environment, and that will match this root spec with that constraint. And like I mentioned before, you can always edit the spack.yaml file directly. And you'll see that it's referenced here, the removal of the root spec from our environment. So before we get to using these files to recreate and reproduce environments, let's do a quick review of spack.lock. So we've mostly been editing the abstract representation of an environment, but Spack also generates the corresponding spack.lock file, which is the concretized version of spack.yaml, and represents the full concretized state of the environment with all the provenance. And because it's designed to be machine readable, it's not exactly easy to read. So we're going to use the JQ utility that's already pre-installed on your VM and should be available within the container as well to read the first 30 lines of spack.lock. So let's do spack.lock and then pipe and then head first 30 lines. So you'll see here that we have some metadata about the version of the lock file. We have the version of Spack that we're using here, and then we have our registered root specs and some metadata about the concretized spec here of OpenMPI. So there are almost 2,000 more lines of information available within this spack.lock file, which you can go read, but we won't get into in this tutorial. So let's get to reproducing an environment. So depending on the granularity and depending on what machine you would like to reproduce an environment on, you can either use spack.yaml or spack.lock to reproduce the state of an environment. So an approximate build is created using spack.yaml. because Spack.yaml does not have the concretized state of your root specs, right? So we can use the Spack env create command to reproduce an environment either from Spack.yaml or Spack.lock. So to demonstrate the use of reproducing an environment from Spack.yaml, let's create an environment called abstract. So let's run Spack env create abstract Spack.yaml. So when we activate this environment with Spack env activate, my project, abstract. And if we look for if we run Spack find to see if any specs have been installed here, you'll see that OpenMPI and Trillianos are not installed because they haven't been concretized and Spack isn't aware of any existing installations of them within the Spack instance. What if we wanted to have an exact reproduction of the original build? You can use Spack.lock for that. So we're going to do a similar thing here by running Spack env create with the name of the environment being concrete, and then Spack.lock. Let's activate the environment here by running Spack env activate concrete, run Spack find, and as you'll see here, Spack find will show OpenMPI and Trillianos as having already been installed. All their dependencies are available here, and yeah, it's essentially an exact reproduction of what we had installed within our independent environment. And the reason why this works is that when Spack picked up the concretized, when Spack inspected Spack.lock and extracted the hashes from that file and sort of use that information to create this environment and have those root specs and have the dependencies listed here, it was able to find those installations within the greater Spack instance, because as you saw before, we've already installed the OpenMPI and Trillianos. So depending on the level of reproducibility that you would like, if you would like to move, if you'd like to reproduce an environment on a completely different machine that has different architecture, that might have maybe GPUs or some other sort of constraint that might influence what type of packages, what type of dependencies are getting installed, Spack.lock won't work for that to reproduce your environment because it requires you to be on the same type of machine. But if you took a Spack.yaml file, reconcretize it on that other machine, it would output theoretically a list of specs and therefore dependencies that fulfill the constraints necessary to install the software on that system. And before we finish the tutorial, I want to make sure that everyone runs Spack env deactivate so that we don't mess up other sections of the tutorial. So please make sure to run Spack env deactivate or despacktivate. So this only scratches the surface of environments and what they can do. Like I mentioned before, they are sort of the bread and butter of advanced Spack features. So Peter will talk about config, and Spack stacks will be talked about tomorrow. And essentially they can be used for many different ways, and sort of set the path to more advanced Spack usage in the future, and can be used for whole sorts of things. Thank you.
I'm just going through some initial setup. If you should see on one side of the screen my terminal, on the other side the configuration tutorial. If you haven't done any of the previous sections, there's instructions at the beginning to essentially do this part of the tutorial. So you don't have to have done anything previous. If you have any questions about that part, please put them in the chat. But otherwise, we will get to it. So there are a ton of things you can configure about Spack. We've already gone over like Spack's concretization process. And to do that, you give it a very usually you give it a pretty terse description of what you want, and it will turn that into like a completely detailed description of everything that needs to be installed, like the versions of things, the variants you set, all the dependencies of everything. And so to expand or to go between that terse and detailed description, it has to make a lot of assumptions. And everywhere that an assumption is made, we've tried to make it so that Spack makes a sensible sort of default assumption, like you probably want to install the latest versions of things. I mean, just in terms of a default. We have in the package descriptions themselves, you might have already seen, you can set like, well, you do set default values for all the variants. So that's just, and Spack will attempt to always respect the defaults. But inevitably, for specs and installations, you will have differing opinions, and you might find it. You can essentially anything about the spec you could theoretically you could put on the command line. If you find yourself doing that multiple times, then configuration I think would be of interest to you. And there's also like a ton of other behavior you can customize in Spack with configuration. So setting things like build parallelism, and also essentially interfacing with some of Spack's behavior is ultimately going to be like only available through configuration. So we broadly divided into what we call sections. This lists out a few of the most prominent ones. This tutorial in particular will be getting a lot into packages configuration, but you can also use the configuration system to customize like LMOD and TCL modules. You can the binary cache that we use for the tutorial is described in a configuration file, and the commands we use to examine the configuration can be essentially used to examine like any of these. And then at the very end of the tutorial, we'll be going over like a kind of a catch-all configuration section that we call config. And we have more. So broadly, we'll be going over scopes, which is a notion of like prioritization for when you want to layer configurations. We'll be going over the general format. All the configuration files follow like a similar layout. And so by interacting with a few, I think this tutorial will provide like a good foundation for like if you ask any question in the Slack channel or wherever, and we talk about modifying the configuration. I think even if we haven't covered it specifically here, mechanically it'll end up looking pretty similar to the examples in this tutorial, and then we'll be having quite a few examples. Let's see. And yeah, the hands-on examples will be building up in a few cases the one of the configuration sections, the packages configuration, from more or less from scratch. So we can examine. I think we said like one of the, or I don't know if I said it explicitly, but one of the sections is about the concretizer, which again is what takes the specs, fills in all the details. You can examine this section with Spack config blame, which tells you, so everything on the left is the files where these values are pulled from, and then it's like, what is the final configuration? I mentioned there's a notion of scopes and prioritization, so Spack config blame will tell you the end result of like all the merged configuration. So if you're worried about two configurations fighting each other, then Spack config blame will tell you ultimately what Spack is seeing. For this tutorial, we want to disable reuse. That's just gonna make some of the concretizations easier, and so we can actually modify that by running spack config add concretizer reuse false. And I think this is a good time. I think this is a fine time to talk about the overall structure. It's a nested dictionary. Ultimately, the leaf values can be like scalars, like true or false, or integers, like 1 or 2. You can also have lists. I don't think there's any examples in here, but we'll be getting into quite a few examples where like the end values are lists. So anyways, we'll set this. We can re-examine it. See the outcome that we have disabled reuse. So now we'll get a little bit more into scopes. You can actually see that kind of in effect here in config blame. We're only showing 2 in this case, but we have the defaults, which is essentially you get clone Spack, and that's we describe sort of kind of how Spack should behave, and because it's the default behavior, that forms the name of the scope. And then we just added our own config, and by default, that gets dumped into your home directory. So these are 2 examples of scopes, and there's a notion for all of these scopes of prioritization. So, and we try to make that sort of a sensible resolution. So configuration that you dump into your user directory overrides things that are in the defaults. They override, there's also another scope in etc. Spack, etc. Spack, that that the user configuration overrides the environments that Caetano just showed you. Those are considered higher precedence than either of those. And then finally, there's like kind of a we assume that if you specify configuration on the command line, that's what you really want to have precedence. So that is the highest priority scope. And we spoke a little bit about the YAML. Maybe I didn't say YAML specifically, but nested dictionary in YAML is the format of every configuration file. There is one deviation from like normal YAML syntax, which is that because this is a nested dictionary and we just talked about scopes and layering, there's also a notion of indicating that we want to override a prior scope. So for merging, for dictionaries at 2 different layers, we can normally merge them. There are overrides in some cases when the values, when you have like the same key value pairs at the leaf, there's not really anything to do except override. For items that are lists, or if you're specifying different things, like we'll be getting into compiler configuration, and if you describe compilers at 2 scopes, Spack would normally merge them. But you can use this double colon syntax to override at a higher scope anything from a lower scope. So we've already seen Spack config blame, and so I also mentioned that the sort of the catch-all configuration section is called config. So Spack config blame config. It looks a bit repetitive, but if you run that, you'll see we have an aliases section, which is like where we describe alternative names that Spack is willing to acknowledge for various commands. We can see the double colon syntax in action by running can actually just add it from the command line. I wouldn't normally recommend interacting. We're going to spend a fair amount of time manually interacting with configuration, but this succinctly demonstrates the concept of configuration overrides. So we see I have turned off all the aliases. All right. So now we're going to get into probably one of the more interesting bits of configuration, which is compilers. Those compilers are described in the packages section. If you've been using Spack for a while, this is new. We used to have a completely different section called compilers, but we are trying to treat compilers like anything else. So they are packages and they live in the packages section. We can see the default. I think if you run any of the tutorial setup commands, you will have run Spack compiler find. And what that's going to do is dump compiler descriptions into your packages. And so what you should see is this. If you don't see this, you can run Spack compiler find. If you still don't see that, then please mention it in the chat, but you should see this. And so this configuration describes 3 compilers. There's 2 GCC compilers, and there's 1 Clang compiler. We call it LLVM. This is a little detailed, but I think I mentioned there's nested dictionaries, there's lists of things. In this case, the compilers aren't built by Spack, so they're thought of as externals. And there's a list of 2 of them. In the YAML syntax, that is like this dash, and then we have sort of 2 list items, and each list item is its own dictionary of attributes, which explains like the important properties of the compiler. We have things like, for example, the GCC compilers have C, C++, and Fortran compilers. You might notice that in the Clang case, we don't have a Fortran compiler. So that is meaningful. It means, I mean, like for Fortran-based codes, we can't only use LLVM. We might imagine, though, that we'd like to generally compile our C and C++ codes with Clang and then defer to gfortran for our Fortran codes. So to do that, there's another configuration section called toolchains. We can add the following toolchain. This is also a little involved, but essentially, like if we go down and look at the example, we're saying use Clang or LLVM as our C and C++ compiler, and use GCC as the Fortran compiler. Is there, sorry, I see something, maybe someone saw multiple compilers. Is that a thing that we want to raise as an, do we want to discuss it here, or is the discussion handling that?
So David asked, his configuration like yours is only showing 3 compilers, but when he runs Spack compilers, it shows 4, including the Spack compiled one. So do you want to talk about, I guess, the fact that these are externals versus internally installed?
Sure. So the configuration will list is only for listing system compilers. And so Spack config blame compilers will only show you those system built ones that have, like if you did Spack compiler find, that's all it will show you. I guess, yeah, Spack compiler list is showing, like, if you install officially a compiler in Spack, it's not registered in the config, it's registered in Spack's install database. If that doesn't resolve it, let me know. All right. Okay, hopefully I think I mixed my quoting things. Maybe we'll have an opportunity to look at what a configuration error would be. So we can use a tool chain like a compiler. I think previous examples in Spack have showed like a spec where you say, the spec name, and then you can, to specify a compiler. The percent is actually more general than that, but it is used among other things for saying you want to use a specific compiler. And we should see OpenBlast happens to depend on all this stuff. So the result should be that we get mixing. Okay, sorry, it's a little split up on my screen, but right here we have like Fortran, which the language, like essentially languages are modeled like virtuals we've talked about. And so we have this notion of Fortran being a virtual. It's satisfied by GCC compiler, C and C++ satisfied by Clang. I assume we can go a few minutes over. I'm still going to move
We can go a
through.
few minutes over. I'm going to try and not hold us up too late, though.
Okay.
So probably like 1 or 2 minutes when we find a good stopping place.
Okay, I didn't know there was another thing after this. Anyways, so we're going to get into, I'm going to just describe this rather than demonstrate it, because I think I want to get into a little bit more interesting package specification. But like, so we looked at attributes you can specify about compilers. You can say, here's a flag that you always want to attach. So like when a spec is built with a specific compiler, add these flags to the compiler invocations. You can run this yourself in the tutorial if you want. I'm skipping past it. If you see something that doesn't look like this, let me know. Probably explain what's going on. And then get a little bit more detailed. We have, you can specify modules. You can specify environment modifications, like setting environment variables, adding R paths. I think we spoke briefly about R pathing. Sometimes for compilers built outside of your, like, say, user, there might be libraries they should be adding, but don't by default. So you can specify that with extra R paths. And there's a bit more description about like, kind of what all that means here, but I think more or less that covers it at a high level. So if you run, oh, sorry, now we're into packages, sorry. So I think at the beginning of this, I said, Spack expands your terse description into a detailed description. So now we're kind of going to get into the, like a little more interesting how to influence Spack's decision-making process about packages. You can see the default settings by running this command. This will no longer exist. You should not see that. That's a mistake on my part. The rest of this, the defaults are approximately like what you should see. They set things like default providers for each virtual, and they also mark certain packages that you would never expect to have to install as not being buildable. So that just avoids certain types of errors. So for starters, we can see what sort of a vanilla concretization of HDF5 looks like. It will, just in this example, it'll pick the GCC compiler. It will pick OpenMPI. These are just based on internal weighting decisions. At some level, we want to be consistent about what we concretize each time. So like even things that you might not imagine caring about assigning like an order to, we generally impose an ordering on. Now versions and things we do like make more sense in terms of preferences. This is a little truncated, but we have our GCC. I guess we already installed it. We have GCC and OpenMPI. We disabled reuse, by the way, so this happened to pick something that was already installed. It's not with reuse disabled, Spack won't be encouraged at all to pick things that exist already. We can create an environment like we saw in the last section, but here we'll basically only be using it to look at the outcomes of concretizations. You can call this anything you want, by the way. It doesn't have to be called this. But we're going to add the following to sort of steer the concretizer. We could like add these types of demands as details on the command line. Although, let's see. When it comes to like transitive details, it's generally much more convenient to specify it like this. So we're going to say there's a way to say it has to be LLVM or Clang. Here we're just saying we'd like it to be, and also we're going to require that the MPI implementation is mpitch. And then we will re-execute. Which should essentially pick an mpitch implementation, and the result you should see is it choosing the Clang compiler. The Clang, like I mentioned, the Clang detail was a preference. If you did not disable reuse, you might see actually it chooses GCC still. Okay, let's see here. We chose Clang. We chose mpitch. So things so far we're changing a couple of details, and this would apply. Those details would essentially apply for any spec. So now anything that depends on MPI, it has to be mpitch, and anytime we're using a compiler, we saw that several are described, but we're preferring Clang. Now we can look as like HDFI was kind of a toy example to demonstrate more about the dependencies in the compilers, but we could ask about HDF5 itself. We might want to apply requirements to that. Maybe we have a project that depends on HDF5, but we don't need the MPI support. Building MPI could take a fair amount of time. I don't know. You might have your own. I mean, if you're on a cluster, you're probably going to have your own MPI. You don't want to build it. We'll look into that later, like using system ones. I have 4 minutes, so you can ask me, or we can get into it later. So we'll get into this quickly. We can turn off that variant. We'll see the spec will get a bit simpler. Okay, cool. Yeah, now we're getting into externals. That's good. I want to cover this in the last few minutes. So anyhow, we should see that this chooses MPI. We'll also see, and we saw in the example above, that we're building CMake and we're building curl. Most times when you're on a system, certainly most clusters, you'll already have like a system install of CMake that is going to work perfectly fine for your example. In this case, we're going to demonstrate like you can, for anything where you don't really want Spack to install it, you can add an external definition. It actually looks similar to the compiler definitions, although the compilers are more detailed because their properties there's more properties that need to be specified. But you can we'll add an external for curl. You could add one for CMake or anything in this list really. Anyhow, we turned MPI off. Now we're not building it. That's great. We also don't want to build, like we need curl. I mean, imagine we didn't have CMake. We need curl, but we do have it on the system, so we don't want Spack to install it. So for that, we can Spack external find curl. There's one additional thing, and I'm going to run the help here to demonstrate an argument. So we did not set this by default. This option is useful in this case because we want to tell Spack like you really do not need to build curl, and we're going to be pretty strict about that. And if you feel that way when you run Spack external find, you can add this argument. In this case, we didn't, so we'll just go back in and say, so we have, after running that Spack external find, this popped up, and we can add before or after buildable false. That just says don't build it. I say before or after because that's the dictionary structure. These are just dictionary keys. Then we shouldn't get a curl. Can you set priorities for the system to use packages or modules installed by Spack, but not others? For example, use curl install with Spack, but still use wget from the system. Well, yeah, I think the answer here is simple. It's like Spack will only use externals that you like explicitly define in the config, and otherwise, it's always going to try to install things itself. I think does that answer your question, Omar? Let me know. Okay. Do you feel like you can expand on that? Or does anyone on the Spack team think they have a notion of more specifically what's being asked?
I think for the externals question, you answered it exactly correct. Spack won't go using anything on your system, for example, libraries or externals, it will always prefer something inside of Spack unless you explicitly define an external. For the question on multiple versions of Spack rather than environments, are you asking about like the packages repo? You can pin an environment to use a specific commit of a packages repo. As for using a single environment over multiple versions of Spack itself, yes, you can absolutely do that. You can continue using an environment as you upgrade Spack.
Install curl and wget in a SpackEnv. I assume all entirely with Spack. And then you want to use the Spack installed packages inside the Spack environment.
So yes, you can do that. Like the way that environments render out views is essentially that. So the packages that are going to be put into your path are only the ones that are in the environment. So if you deactivate the environment, Spack will go modify your path. So none of that will be in your environment anymore. And then when you go activate an environment, it'll load all of that into your path.
Yeah, you could also install a package with Spack in one environment and use an external for it in another environment. That being said, I think Alec someone asked a similar question, I think in the Slack chat. And if both of those environments reference the same Spack database, then pre-existing installs by Spack are not disabled by setting buildable false. Because from Spack's point of view, if it was already installed by Spack, you're not building it, but it's fair game to use. Generally speaking, if you disable reuse, like we did in the tutorial, in the other environment, and you have the external and you set buildable false, you're going to get the external. I don't know if those additional details are useful at all.
I think just to answer Omar's last little bit of a question, yes, what you install with Spack and put into an environment when it renders out that view and modifies your environment, that's going to prepend basically. So everything that you install with Spack will be at the front of your environment and is going to get used first. If you need to pass something in from the system, you would end up making that an external, and then it would get rendered into your path.
Interesting question.
Yes.
Is there? Oh, sorry, Alec.
Oh, sorry. No, I was just going to say yes. There is a way to completely ignore .spack. I can find the documentation right now, but if you go to the Spack docs and you look up isolating Spack or something, we have a page on it. There's 2 environment variables that you can set. That one will disable local config, which is that .spack, and the other one will move all of the caching to a specific location of your choice. And so then all of the configuration is in the Spack instance itself, and in that caching location. So you can isolate and then use multiple versions of Spack simultaneously without them overriding or stepping on each other's toes. Peter, if you want to talk to that more, because I know that you're more involved in that.
Oh, no, I mean, there are ongoing efforts to add other ways to do that, but you've described how it works now. That's good.